Swayam Prabha. Digital India. Educated India.
Hello and welcome to CAD series of video lectures. This is lecture 13 on differential geometry of curves. In the layout, we are in the second column here. Why do we need to study differential geometry or differential properties of curves? Well, as I mentioned in the previous lecture, we are going to be fitting segments of smaller degree through subgroups of these design points. For example, here we have interpolated these points using a cubic polynomial. We have a second subgroup, again of 4 data points, and we have used a different cubic segment for interpolation. This is the junction point, which would be critical in curve design. Here, we would need to ensure position continuity, continuity of slope, and curvature. We would be matching 0 order, first order, and second order information. It is these points in particular that would motivate us to study differential geometry of curves. Now let's draw the Cartesian space and let's draw a curve in space. Let's say we have point P on the curve, another point Q on the same curve. The position vector of P is RU. Remember, we chose to work with parametric representation. And the position vector of Q is RU plus delta U. This vector here is the difference vector, delta R. This bold arrow here represents the tangent at point P to the curve. The tangent is expressed by capital G in bold. We can use the Taylor series expansion and express the position vector of Q, which is R of U plus delta U, as RU plus dr over du, the total derivative of R with respect to U, times delta U, plus 1 over 2 factorial d2r over du squared, the second derivative, times delta U squared, plus there would be higher order terms. For small delta U, delta R will represent the arc length, delta S. So delta S is approximately equal to the absolute value of delta R, which is R of U plus delta U minus RU, which is approximately equal to the absolute value of dr over du times delta U. Here we have ignored the higher order terms. If Q approaches point P, then delta S takes the differential form ds, which is equal to modulus of dr over du times du. This derivative of R with respect to U is denoted by R So ds is the absolute value of r dot times du, and the mod of r dot can be written as r dot dotted with r dot square root of that times du. Now, if we wish to compute the total arc length from, let's say, a point P at which the parameter value is u sub 0 to a point Q at which the parameter value is, say, u, then the total arc length is given by s of u, which is equal to integration from u sub 0 to u ds, which is r dot dotted with r dot within the square root sign times du. And if r is expressed in terms of scalar functions x of u, y of u, z of u, then r dot will be x dot u times I plus y dot u times j plus z dot u times k. R dot dotted with r dot is given by x dot squared plus y dot squared plus z dot squared within the radical sign du. So this integration can be computed to get the overall arc length. Continuing further, parametric velocity bold v is given by the first derivative of r with respect to u, or r dot u. The unit tangent t is along the direction of the parametric velocity v. So capital T bold is given by r dot u over the absolute value of this, which is equal to dr over ds. Now the first derivative of r with respect to s is represented by r prime s. S, as we have seen before, is the arc length parameter or the natural parameter. Question: how do we get from here to here? Let me explain this to you on board. Okay, so we have seen that the unit tangent t equals vector r dot u over the absolute value of the same vector, which is equal to dr over du over the absolute value dr over du. You have seen from before that ds is equal to dr over du, the absolute value, times du. If we plug in for this value here, we will get dr vector over du. Here we'll have ds, here we'll have du. These will cancel. This would be dr over ds, which is r prime s. Recall that we are using the dot notation to represent derivative with respect to u, and we are using the prime notation to represent derivative with respect to s. Now r dot is equal to dr over du. By chain rule, this is equal to dr over ds times ds over du. dr over ds is r prime s, ds over du is the absolute value of the parametric velocity, r prime s is the unit tangent t times the magnitude of the parametric velocity. Let's take an example. Find the length of a portion of the helix given by x equals a cosine of u, y equals a sine of u, and z equals b times u. A is the radius of the helix, b is related to the pitch, and u is the parameter. All we need to do is we compute x dot, derivative of x with respect to u, derivative of y with respect to u, and derivative of z with respect to u. X dot equals minus a sine u, y dot equals a cosine of u, z dot equals b. Note, in the parametric form, r of u is a cosine of u times I plus a sine of u times j plus b u times k. X dot squared plus y dot squared plus z dot squared can be determined to be a squared plus b squared. We have seen before how to compute the arc length. S equals, here we have taken u sub 0 as 0, integration from 0 to u under root of x dot squared plus y dot squared plus z dot squared, which is under root of a squared plus b squared times du, and clearly this integration turns out to be a squared plus b squared within the radical sign times u. What we observe here is an alternative way to represent a helix using a different parameter, s. Note that this equation relates s with u for this helix. All we can do is substitute for u and write this expression in terms of s as a cosine s over under root of a squared plus b squared times I plus a times sine s over under root of a squared plus b squared times j plus b times s over under root of a squared plus b squared times k. This expression and this expression, they are all u. It depends on our convenience whether we would want to choose to work with parameter u or parameter s to compute different differential properties of the curve. The normal and the binormal at a point on the curve. Normal is given by n and the binormal by b. Well, we have this curve, we have a unit tangent t, and we have a plane which is perpendicular to this unit tangent at some point p. This plane will be spanned by two vectors, both of which will be orthogonal to each other and also orthogonal to the unit tangent t. This is the first one, represented by n, and this is the second one, represented by b. N is called the normal and b is called the binormal. The plane containing the two normals N and B is called the normal plane. The plane containing the unit tangent and the binormal is called the rectifying plane. And the plane spanned by N and T is called as the osculating plane. If you consider 2 points very, very close to this point, as we know, a circle can pass through 3 points, we can construct a circle that passes through these points. The circle is called the osculating circle. Notice that the normal points towards the center of the circle. As I said earlier, this osculating circle passes through 3 very close points on the curve where the tangent T is defined. Some more on the normal and binormal. Normal N, how to compute that? Well, we have T, which is evaluated as dr over ds, in short represented by r prime of s. At a point very close to this point, we'll have T of s plus delta s, which can be computed as r prime at s plus delta s. Let's see how the direction of the unit tangent changes. You have this curve, you have ds, here the unit tangent at some point, and then at a point very close to this point, we have another unit tangent, T of s plus delta s. What we do is we move ts so that the tips of these two tangents, they join. This vector here represents the difference vector, n equals ts plus delta s minus ts. Notice that this is ts. So n is delta t of s, which is t of s plus delta s minus ts. We can use the Taylor series expansion to expand this expression, t of s plus dt over ds times delta s plus some higher order terms minus ts. These two will cancel out, and if we ignore the higher order terms, delta ts will be approximated by dt over ds times delta s. For 2 points very, very close to each other, delta t over delta s will take the differential form dt over ds, which will be given by r double prime s. Remember that we are using the prime notation to represent derivatives with respect to the natural or the arc length parameter. Now, we know that t is a unit tangent, and so its magnitude is 1. In a sense, r prime dotted with r prime is equal to 1. If we differentiate this equation with respect to s, we get r prime dotted with r double prime plus r double prime dotted with r prime equals 0, which implies eventually that r prime dotted with r double prime is equal to 0. What would this mean physically? This would mean that r double prime is a vector which is orthogonal to r prime. R prime is our unit tangent, T. In other words, R double prime will be orthogonal to the unit tangent, T. We can use this fact and define the normal n such that some scalar kappa times n equals R double prime, which is dt over ds. Kappa is a scalar used so that n happens to be a unit vector. Here, kappa is a scalar and n is a unit vector. Finally, the binomial B is given by the cross product between the unit tangent and the unit normal. We know that both T and N are orthogonal to each other. It is the scalar kappa that we need to investigate a little further. Question: what is kappa? Does it have any physical relevance or significance? We have a curve here. This point is P with position vector RU. This point here is Q with position vector R of U plus delta U. This is point W with position vector R U minus delta U. Now P, Q and W are points very close to each other. We can say they all lie on the perimeter of the oscillating circle. Now, let's compute QP crossed with QW. QP crossed with QW. QP is given by R of U plus delta U minus RU, and QW is given by R of U plus delta U minus R of U minus delta U. We use the Taylor series expansion and consider terms up to second derivatives. RU plus delta U will be RU plus dr over du times delta U plus half of d2r over du squared times delta U squared. The term Ru gets cancelled with this. So these two terms are what? Which are left, and Ru plus delta U minus Ru minus delta U, when both expanded using Taylor series, will give us 2 times dr over du times delta U plus 2 times d2r over du squared times delta U squared. Let's try to simplify this cross product further. Well, what happens if this term gets crossed with this term? Note that the direction of dr over du is the same in both terms, so the corresponding cross product will be 0. Next, this term crossing with this term will have 2 times dr over du crossed with d2r over du square times delta U q. Now, this term crossing with this term. This half cancels with this 2. We'll have d2r over du squared crossed with dr over du. If I reverse the two terms around the cross product, I will introduce a negative sign. If we further work out the algebra, this cross product will reduce to dr over du crossed with d2r over du squared times delta u cube. Now, we know that the unit tangent is given by dr over ds, which is r prime s. This would imply, using chain rule, that dr over du is equal to t, the unit tangent, times ds over du. All I need to do is multiply and divide this expression by du and rearrange this equation to get this result. Now, if I compute the second derivative of r with respect to u, that is, if I differentiate this expression again with respect to u, I get d2r over du squared, which is equal to dt over du times ds over du plus t times d2s over du squared. All I can do now is replace this term here by this term on the right hand side of this equation. Therefore, QP crossed with QW is given by T times ds over du. Notice that I am replacing dr over du as well by this expression. So T times ds over du crossed with dt over du times ds over du plus T times d2s over du squared. This entire thing times delta u cube. If I work on this cross product further, I notice that the direction of this term and this term, the two directions are the same, so the corresponding cross product is 0. So what is left is t crossed with dt over du, which is this term and this term, times ds over du the whole square, these two terms getting multiplied, times delta u cube. Now, let's see how this term can be written in terms of the other normals, n and b, the normal and the binormal. Well, as you see, we retain this scalar ds over du cube here. We know from before that dt over ds is kappa times n. So we see these two terms here, kappa n, and we retain this term t here. So this expression becomes kappa times t crossed with n times this scalar ds over du the whole cube times delta u cube. And t cross n is the binomial b. In other words, QP crossed with QW now is kappa times the binomial vector B times the scalar ds over du the whole cube times delta u cube. Let's retain this result. We are going to be using this in the next slide. Back to this figure here. We have a curve and points P, Q, and W with position vectors RU, RU plus delta U, and RU minus delta U. Using vector algebra, the radius of curvature is given by rho, which is equal to modulus of vector WP times modulus of vector WQ times modulus of vector WP minus WQ, WP minus WQ over 2 times modulus of the cross product between the vectors PQ and WQ. Well, we can compute these vectors in terms of the corresponding position vectors. This looks a little tedious. Let's try to work it out. Rho equals the mod of WP, which is delta U times dr over du minus half of d2r over du squared times delta u squared plus some higher order terms. Mod of WQ, which is 2 times delta u times dr over du plus, again, some higher order terms. Mod of vectors WP minus WQ, which is delta u times dr over du plus half of d2r over du squared times delta u squared plus some higher order terms. These expressions can be obtained using Taylor series expansion with some additional algebra. The denominator is given by 2 times dr over du crossed with d2r over du squared, the modulus of that, times delta u cube. You may want to work as an exercise as to how the radius of curvature is computed using this expression. Now, starting with this complicated looking expression, rho can be simplified to be delta u cube times dr over du, the absolute value, the cube of that, over dr over du crossed with d2r over du squared, the absolute value of this, times delta u cube. We see from this expression that delta u cube can get cancelled out, and so rho becomes modulus of dr over du the whole cube over modulus of the cross product between dr over du and d2r over du squared. From the result in the previous slide, we can replace this expression and rewrite this equation as rho equals 1 over kappa mod of dr over du the whole cube over ds over du the whole cube. and noting that mod of dr over du is the same as ds over du, the two terms get cancelled out, and so rho is equal to 1 over kappa. So kappa, after all, has some physical significance. It's called curvature, and it is the inverse of the radius of curvature, rho. Next, torsion, another differential property of curves. We know that the binomial b and the tangent t are orthogonal, so b dotted with t equals 0. What we can do is we can differentiate this result with respect to s to get t dotted with db over ds plus b dotted with dt over ds. The right hand side is going to be 0. And we can use the definition dt over ds equals kappa times n and substitute this expression here. What we find when we substitute this thing here is that b dotted with n will be 0, which would make t dotted with db over ds equals 0. Right here, t dotted with db over ds equals 0, which physically implies that the first derivative of binomial with respect to the arc length is orthogonal to t. Also, if we differentiate b dot b with respect to s, we will see that b dotted with db over ds equals 0, implying that db over ds is orthogonal to b. Interesting. db over ds is orthogonal to t, and also db over ds is perpendicular to b. dB by ds, therefore, is bound to be aligned with the unit normal n. We can use this fact to define dB over ds as minus of some scalar tau times the unit normal n. This scalar tau is known as torsion. Using the fact that the unit normal n is expressed as the cross product between the binomial and the unit tangent, we can write dn over ds as dB over ds crossed with t plus b crossed with dt over ds. Following the algebra further, the right hand side here can be written as dB over ds crossed with t plus, well, we can use the definition here. dt by ds is kappa times n. So this term here is kappa times b crossed with n. Now this term here can be replaced by this term here. So we get minus tau times n crossed with t plus kappa times b crossed with n. N crossed t is minus b, and b crossed with n minus is t. So dn over ds equals tau times the binomial minus kappa times the unit tangent. In summary, we get four relations. Number one, dr over ds is defined as the unit tangent t. dt over ds is defined as scalar kappa, which we have seen to be the inverse of radius of curvature, times the unit normal n. dB by ds is defined as minus of tau times n. The scalar tau is called the torsion. And dN by ds is tau times the binomial minus kappa times the unit tangent. If you see the left hand side of these relations, r, t, b, and n, the left hand sides express the first derivatives with respect to s, and the right hand side respectively express the corresponding results. These four relations are known as Frenet-Serret formulae. In subsequent lectures, we are going to be using these relations to compute the differential properties of curves at different points.